Section 16.5, Curl and Divergence. So in this section, we're going to talk about two different operations that can be performed on vector fields. And these are going to be really helpful. While we're not going to get into the applications right now, we're just talking about the mathematics. But if you end up doing anything later in your academic careers with fluid flow, electricity, or magnetism, all of these are going to apply. So each of these operations is sort of like differentiation. So we're doing a lot of partial derivatives here, but one produces a vector field, whereas the other produces a scalar field. Now remember, to produce a vector field, one way to get to a vector is to take the cross product. That's what we're going to do today. To get to a scalar field, we are going to use the dot product. And just a reminder, when we talk about a vector field, our general notation is going to be this capital bold F. And because we can't really write in bold, we can put this little vector arrow on top of it. And so if we've got F, so this is some vector field, we can tell that it's a vector because it's got I, J, and K components. And it's a vector field on 3 dimensions, this r cubed, meaning 3D. And the partial derivatives of p, q, and r all exist, then the curl of F is the vector field defined by this equation. Now this equation is a little bit complicated, and we don't want to have to memorize anything like this. And so we've got a significantly easier way to do this. But first, let's talk a little bit about this del operator. Now, when we've seen this operator before, we've thought immediately gradient. But now we're going to call this del. And this del operator is just saying that what we're doing is taking the partial derivative with respect to x of the I component, the partial derivative with respect to y of the j component, and the partial derivative with respect to z of the k component. So essentially, we're just taking each of these components' respective partial derivative. And so if we take del of f, another way we can kind of look at this is if we're multiplying del and some vector function, then we end up with the gradient. And so we can say that del f is equal to the gradient of f. All right, we just want to specify this because now we're just going to talk about that del, not necessarily the gradient. And so this brings us to our definition of curl as we are going to use it. And so we can say that the curl of f is del cross product this vector function f. So that's our definition for curl that we're going to use. This del is just these partial derivatives of x, y, and z, and then this vector function f for our vector field is just going to have those components p, q, and r. And this is exactly that formula that we saw on the first page for curl. And you can use this, go ahead and use this. But I think it's a little bit easier to use this determinant just to find the cross product. And so we can get the curl of f, which is equal to del cross product the vector function or the vector field function of f. So a few things to note here is that lowercase f of x, y, and z has continuous second order partial derivatives. If this is true, then the curl of del f is equal to 0. This leads us to the conclusion that if f is a conservative vector field, then the curl of f is equal to the curl of del f, which is equal to 0. Because remember that a conservative vector field means that there exists some function for which, in this case, we're talking about the gradient of f, because remember, we said del f is the gradient of f, is equal to this vector field f. So if this is true, then the curl of del f is also equal to 0. I'm sorry, the curl of this vector field f is also equal to 0. And so in number 3, we can then conclude that if f is defined on all R3, whose components have continuous first-order partial derivatives, and the curl of f is equal to 0, then f is a conservative vector field. And so while this isn't very easy to verify, number 2 and number 3 are just converses of each other. So it's much easier to show that f is a conservative vector field if we can show that the curl of f is equal to 0. That's what we're going to do today. And so example 1, we want to start by just finding the curl of f. If f of x, y, and z is equal to xzi plus xyzj minus y squared k. So starting off with the curl of f. And we said that the curl of f is just equal to the cross product of del and f. Remembering that we can find the cross product using this determinant of I, j, and k, and that we're taking the cross product. Remember that the order in cross product does matter. And so this next line is just going to be the components of del, which are the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. Next, we just have the components of f, which were given as xz, xyz, and negative y squared. And so when we compute this, we can say that this is equal to, remembering that what we're doing is we're looking at this I component, and we're imagining that we're crossing out this row and this column that includes I. And then we're forming this two-dimensional discriminant and taking the multiple of the product of this diagonal minus the product of this diagonal. So for our first diagonal, we get the partial derivative with respect to y of negative y squared. And so we can look at this as the partial derivative with respect to y times negative y squared minus the partial derivative with respect to z of xyz. And yes, when we take this partial derivative of an expression, it's like multiplying. We've got the same operation going on here. We're subtracting that j component, remembering that this negative is just part of our three-dimensional, our cross product here. Cross product's always three-dimensional. So just part of our cross product, and we've got the partial with respect to x of negative y squared minus the partial with respect to z of xz plus our k component, which is the partial with respect to x of xyz minus the partial with respect to y of xz. Now we've just got to simplify. And so the partial with respect to y of negative y squared is just, well, the derivative of this normally, if we're talking about y, which is negative 2y. So we've got negative 2y minus the partial with respect to z. Treating x and y as constants, we will just be left with an xy. So this is our I component, minus the partial with respect to x of negative y squared. Well, with respect to x, y is just a constant, and the derivative of a constant is 0. The partial with respect to z of xz, treating x as a constant, is just going to be x. That's our j component, and as for our k, we've got the partial with respect to x of xyz, treating y as z and z as constants, leaving us with just yz. We're subtracting from that the partial with respect to y of xz. Because x and z are both constants in this case, this is just going to be a 0, and that is our k component. And so finally, we can rewrite this as the curl of f is equal to the quantity negative 2y minus xyi minus a negative xj, so plus xj, plus yzk. And so this is our curl. And so in question, in section B, we're asked if the vector field is conservative. So for B, is the vector field conservative? Let's refer back to our notes. If the curl of f is equal to 0, then f is a conservative vector field. So if these have continuous first order partial derivatives, which we're not really going to test here, we're just going to test the curl of f being equal to 0, then f is a conservative vector field. So let's check. Is this equal to 0? No, this curl is not equal to 0 because the curl of f is not equal to 0. Therefore, f is not a conservative vector field. And so this is the way we're going to determine if a three-dimensional vector field is conservative. Let's just make a note here because two-dimensional vector fields are different. Remember what we did for two-dimensional vector fields? So in R2, we determined if a vector field is conservative by setting the partial of P with respect to y equal to the partial of q with respect to x. In R3, we are going to set the curl of f equal to 0. So if this is true in R2, then this vector field is conservative. If this is true in R3, then this vector field is conservative. So we've got a different process for these two-dimensional and three-dimensional vector fields. So just to determine if these are conservative. So example 2, determine if the vector field f is equal to x squared yi plus xyzj minus x squared y squared k is a conservative vector field. Because this has I, j, and k components, this is in 3 dimensions. Therefore, we're going to find the curl of f. And so the curl of f is just the cross product of del and f, which is equal to this determinant of I, j, and k of the partial with respect to x, so the components of this del, the partial with respect to y, and the partial with respect to z, cross product with the components of f, which are x squared y, xyz, and negative x squared y squared. And so we can say that this is equal to I times the quantity of the partial with respect to y of negative x squared y squared minus the partial with respect to z of xyz minus our j component, which is the partial with respect to x of negative x squared y squared minus the partial with respect to z of x squared y. Finally, we've got our k component, which is the partial with respect to x of xyz minus the partial with respect to y of x squared y. All right, let's continue. The partial with respect to y of negative x squared y squared is going to be, treating x as a constant, a negative 2 x squared y. Partial derivative with respect to z of xyz is just going to be xy. And so this is our I component. Now, we could find the j and k components, but there's no need to continue. Because look, negative 2x squared y minus xy is not equal to 0, right? And so if my I component isn't equal to 0, then it doesn't really matter what the j and k components are, because neither of these can possibly make the I component equal to 0, because this is a vector, and I, j, and k components are separate. And so because this does not equal to 0, well, we can automatically determine, we can stop here, since our I component is not equal to 0, and determine that F is not a conservative vector field. And this is our conclusion. One more example of this. Let's show that this vector field is conservative. So we're given that it is conservative, and we just need to show it. Meaning for part A, we just need to find the curl of F. And we know that's the cross product of del and F. And so let's just set this up. We've got our I, j, and k components. We've got our del, which is the partial with respect to x, the partial with respect to y, and the partial with respect to z. And we've got our y squared z cubed. We've got our 2xy z cubed. And we've got our 3x y squared z squared. All right, now I'm going to kind of skip a step here, because I know my I component is just going to be the partial with respect to y of 3xy squared z squared. So I'm just going to take the partial derivative with respect to y of this expression. And so with respect to y, this partial derivative, treating x and z as constants, is going to look like 6x, y, z squared. Subtracting from that the partial derivative with respect to z of 2xyz cubed, treating x and y as constants, that's just going to look like 6x, y, z squared. Minus our j component, which is the partial with respect to x, of 3xy squared z squared. And so treating y and z as constants, this is just going to look like 3y squared z squared. And subtracting from that the partial with respect to z of y squared z cubed, which is going to look like 3y squared z squared. And finally, the k component is going to be the partial with respect to x of 2xyz cubed, which is just 2yz cubed, minus the partial with respect to y of y squared z cubed, which is 2y z cubed. And so simplifying this, we're told this is conservative. So we're essentially told that the curl of f is probably going to be equal to 0, and that's exactly what happens. The I component, 0. J component, 0. K component, 0. And because the curl of f is equal to 0, yes, this is conservative. And so if this is conservative, and only if this is conservative, we can find a function f such that, I'll fix this in the notes, this is supposed to say f is equal to del f. There we go. All right, so now for part B, we're finding this function of f. And we're remembering that we have this process because in this case, we're given the gradient. We want to find the original function. Okay, and so let's start off with this I component. We're going to take, because this is the partial derivative with respect to x, because we're given that the partial with respect to x of x, y, z is equal to y squared z cubed, I want to get to the original function by taking the integral with respect to x, just undoing this partial derivative. And so the integral with respect to x of y squared z cubed, so that's going to look like y squared z cubed dx is going to be our original function, f of x, y, and z, which is equal to, well, this is just going to look like an x, y squared z cubed. Now we have this constant of integration. Because we only looked at the I component, this constant of integration could contain both y and z components. And so that's why I'll call this a g of y and z, so some other function of y and z. Now to solve for this constant of g of y or z, I'm going to take the derivative of f with respect to y, because we're given that that's 2x y z cubed. So the derivative with respect to y of x, y, and z is equal to, well, this is going to be 2 times x, y, z cubed plus, and this derivative is just going to look like a g prime of y and z. We're just taking the derivative with respect to y. Now let's look at this second component here, 2xyz cubed. Because we're given that our partial with respect to y of x, y, and z from the problem is 2xyz cubed, by setting these two equations equal to each other, I can see that this derivative, this g prime of y and z, is supposed to be a y and a z must be equal to 0. If this is true, then g of y and z is just equal to some constant. And so now let's see if, now that we've sorted out the y part of it, let's see if there's potentially a constant that's a function of z. And so we're using this same function that we used to get this partial with respect to y. And now we're finding the partial with respect to z of x, y, and z. This time treating x and y as a constant, we get that this is going to be 3 xy squared z squared plus some function of z. And remembering that this is the partial derivative with respect to z, we know that this is also going to be the derivative of that constant. So let's call that h prime of z. And so to solve for this h prime of z, again looking back at this original vector field, we know that the partial with respect to z of x, y, and z from the problem should be equal to 3x y squared z squared. And isn't this exactly what we see here? Leading us to the conclusion that h prime of z is equal to 0, which means that h of z must be some other constant. We can call that c. We can also just call that some different constant k. And because of this, we have determined that one of the functions f, notice that this is find a function f, not find the function f. One of the functions f contains these constants both being equal to 0. And so we can say a function of f is f. Because it's a function of f, y, and x, y, and z, we can put f of x, y, and z is equal to x y squared z cubed. So this is our potential function. Now we just went over how to find curl. So we said that curl is just the cross product of del and f. But what does it mean geometrically? Well, if we have some point P here, and this point is in 3D space, so it has x, y, and z components. And let's say, for example, that this function f represents the velocity field in fluid flow. So we have some fluid exiting this point P. Say this is a faucet and you're shooting water into a tub of water. And around this point P, you have this circular rotation. Well, that's curl. So if the curl of f at this point is 0, that means there's no circular rotation around this point. Now, you can still have these tiny little wheels moving with the fluid. So that means that I can still have tiny little wheels that might look like this, where the fluid's kind of flowing forward and then curling around itself in this direction, but there's still no circular rotation around this point perpendicular to the direction in which it exits this faucet. So that's what we mean by this tiny little paddle wheel. If the curl of f is not equal to 0, then this paddle wheel would rotate about the axis. We're picturing this as a paddle wheel around this point P. And so we're going to talk more about this idea when we get to section 16.8 and even further down in the section when we talk about divergence. So if this function f, which we said is a vector field, has 3 dimensions, and all of these partial derivatives exist, then the divergence is a function of 3 variables defined by divergence of f is just the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. Notice what happens here. Because we're taking, what does this look like? Partial with respect to x, partial with respect to y, and partial with respect to z. Well, this looks like a whole lot like del. And then when we talk about f, we said that the components of f are just p, q, and r. And so that's how we find that the divergence of f is just the dot product of this del and f. And so now let's find the divergence of f. Well, this is relatively simple. We said that the divergence of F is just the dot product between del and F. And so this is just going to be the dot product between del, which is the partial with respect to x, partial with respect to y, and partial with respect to z, and that with the dot product of f, which is xz, xyz, and negative y squared. Taking that dot product, we're just multiplying the components, and so we have the partial with respect to x of xz plus the partial with respect to y of xyz plus the partial with respect to z of negative y squared. And so partial with respect to x of xz is just going to be z. Partial with respect to y of xyz is just going to be xz. Partial with respect to z of negative y squared is just going to be 0. And so we can conclude the divergence of f is equal to z plus xz. We said in the beginning that we would be performing operations on some vector field so that we produce a vector and a scalar. We know when we take the cross product, that gives us a vector, and we can see that when we take a dot product, this gives us a scalar. Because there are no I, j, and k components, so if z and x were just constants, this would just be a number. And so divergence gives us a scalar. And so now let's talk a little bit about what divergence really means. So if f is a vector field in 3 dimensions, we said that the curl is also a vector field. We said that its divergence was a scalar. And so we can conclude that if f is a vector field on R3 and p, q, and r have continuous second-order partial derivatives, then the divergence of the curl of f is equal to 0. So we can talk about this in the context of fluid flow. So we're going to bring back that diagram where we have some fluid flowing out of this point P. So we have this point P with x, y, and z coordinates. If we have water that is exiting our faucet and we have some curl, and this curl has a direction. And just checking this with our right hand rule, if I hold my hand out, my right hand, and I curl my fingers around this in a clockwise direction, my thumb is going to point out of the page. Great. And so this is our curl. All right, I think I might have said clockwise. I meant counterclockwise there. And so now for the definition of divergence. Well, we know that divergence just means to separate from. When we talk about a divergent series, this divergent series never ends up having a limit of one value. These values either get further apart or just never settle on one value. And so if I have, let's use this example again, if I have some particles of water that are exiting from this faucet, if this function of water flow is divergent, that means that these particles are going to get further and further apart from each other as this water flows outward, which is kind of like what happens if you are white water tubing with your friends and you start off holding hands. When you let go, you're more than likely going to be pulled apart from each other. So there's some divergence there. So divergence is the tendency to pull away from this particle. So we're moving outward. And so if I take the divergence of the curl, Well, because I'm multiplying these two, I'm really just multiplying each of the components because divergence just has the partial derivatives with respect to x, y, and z. And so taking this divergence of curl means taking del times the cross product of del and f. And I know that the dot product of perpendicular vectors is 0. And that's exactly what's happening here. Because I know curl is perpendicular to this actual rotation and divergence just moves away from this point, I know these things really only exist or make sense in 3 dimensions, then I know that the divergence of curl is always going to be equal to 0. If we can relate this back to our scalar multiples of one another, remember we said that the scalar triple product of some A with the dot product of the cross product of B and C equals 0 if these points A, B, and C are coplanar. Well, we're kind of saying the same thing here, that if this function exists in 3 dimensions, and P, Q, and R have continuous second order partial derivatives, then the divergence of the curl is equal to 0. And so when the divergence of some vector field is equal to 0, then F is just said to be incompressible. And again, we're going to talk about this more when we talk about the divergence theorem, which you'll learn about later in this unit next week, I believe. And so let's just do one example of this. We just want to verify that the divergence of the curl of f is equal to 0. So we just want to practice this operation for f is equal to yz squared I plus xyj minus yzk. And so starting off with the curl of f. We know the curl of f is just the cross product of del and f. And we're going to create this determinant of I, j, and k with our del, which is the partial with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And then f with our I component being yz squared, our j component being xy, and our k component being negative yz. And so this is going to be I. Our I component will have the partial with respect to y of negative yz minus the partial with respect to z of xy minus j times the partial with respect to x of negative yz minus the partial with respect to z of yz squared, and plus k. And that k component is going to come from the partial of x times xy minus the partial with respect to y of yz squared. And I know we kind of did this the long way. Just wrote everything out. The partial with respect to y of negative yz is just a negative z. So we've got a negative z. With respect to z, x, and y are constants, and so this is just going to be a negative zi. And our j component is going to be the partial with respect to x of negative yz, which is just 0. Partial with respect to z of yz squared is going to be a 2yz, so minus 2yz. That's our j component plus our k component with respect to x. The partial derivative of x, y is just y. With respect to y, the partial derivative of yz squared is going to be z squared. And we have that the curl of f is equal to, and I'll just write this in that bracket form because I know I'm going to end up using a dot product. It's just a little bit easier to do this way. I component of negative z, j component of a positive 2yz, k component of a y minus z squared. And so now I'm taking the divergence of the curl of f to be equal to the dot product of del and the curl of f, which is equal to the dot product of the partial with respect to x, partial with respect to y, and partial with respect to z. And this curl that we just found, which is the vector negative z, 2yz, and y minus z squared. And so this is going to be equal to, so the divergence of the curl of f. Sometimes you'll see these parentheses, sometimes you won't. It does not matter. And this is just going to be the scalar because when we take the dot product, we know we're ending up with a scalar. Partial with respect to x of negative z is 0. Partial with respect to y of 2yz is just 2z. Partial with respect to z of y minus z squared is going to be negative 2z. 2z minus 2z is equal to 0. And so the divergence of the curl of f, let's just put parentheses to stay consistent, is equal to 0. And that's all there is to it. So just a little bit more theory, and some of this stuff is going to come up later. But we have this differential operator that happens when we find the divergence of the gradient. So the divergence of the gradient of a vector field. In this case, because we're talking about 3 variables here, at least in the case of 3 variables, this is just going to be the components of the partial derivative, the second order partial derivative of xx, second order partial derivative of yy, and second order partial derivative of zz. And this happens a lot in some different physics applications that you'll probably learn about in other courses. And so we call this this Laplace operator. So this Laplace operator, which is this del squared f, or just del squared, or just del dot del, again, all called the Laplace operator. So this happens a lot in physics. And what's kind of interesting here is that we talked about how Green's theorem was just an easier way to evaluate certain line integrals when we have a region that is closed and is smooth or piecewise smooth, and we're traveling counterclockwise. So that's what this symbol means, that this fits into that category. Well, this is equal to the double integral of the curl of f, the dot product of k. When we take this dot product with k, that just means we're only worried about the vertical component of curl over some region D. And there's another version here that says that this line integral of the normal component of f along C is just equal to the divergence of this function f of x and y over this region. And so again, just giving these here for you to be able to make that connection, and we'll talk about some of these later.